All right. So today will hopefully be relatively short because we have to pass back the tests, and it's Halloween and it's Friday, so that's like the triple storm there. But today we're going to talk about belts and belt frictions. When we say that, that's another engineering term for pulleys. So we introduced machines in Module 3 and we analyzed them as a whole, as a structure, because they do what to the input force? They modify it or they transmit it. Okay, they change it. They're not just there to hold it. Okay, and then I promised you that we would analyze machines individually. Okay, and so that's what we started with last lecture in wedges. We analyzed them individually. We kept our methods the same. Okay, where we analyzed individual components. Okay, but we had to take into account friction. Right? Friction changes everything. Way to pass the homework, guys. Good job. Even across the aisle. Did I see that? Bobo did it? Yeah. Careful, don't pass out. Okay. So, I told you, he's going down. Okay. So in analyzing pulley systems previously, all right, can we handle the jokes today or do I have to be mean? Handle it. Okay. When we've analyzed these pulley systems, we've inherently assumed no friction, right? We've never taken into account the contact between the rope and the pulley. Okay, we've assumed that that rope is infinitely small, that it has no mass, and that pulley is perfectly frictionless, right? That's a huge assumption. So now that we are understanding our friction methods, okay, we need to apply those as we analyze these machines that have belts or pulleys within them, okay? So a pulley, okay, the tension within a pulley as it wraps around the surface, okay, is not constant, all right? And so just with your intuition, why do you think that is? Just with your intuition, why do you Reese's that is? Anybody? The surface is changing, okay? If it was a point, okay, if it was a point, that tension would be equal on both sides, right? And that's the assumption that we make. We made that assumption in the last test. But it's not, because that surface is changing, all right? So let's derive why that actually, what that actually looks like in terms of our methods with machines, okay? So if we want to find the minimum force P, okay, the minimum force P in this system that will maintain equilibrium, okay, that will maintain some of the forces equal 0, okay. Just before we even start solving this, is P going to be bigger or smaller than our load? Smaller, why? Kind of, yeah. But what else is going on that we're not taking into account? Friction, right? That friction is holding the load. It's assisting P. What kind do you want, Peyton? Right away. Okay? So friction is aiding the force P, all right? So if we draw the free body diagram, okay, just of the belt, okay? So with machines, we analyze them separately. We have our force, okay, across the surface, 200 pounds, and we have this force P, okay. How do you think we will represent the forces, okay, on the surface of contact? What kind of forces are there? Normal and what? Friction. Okay, so you got half of it, Jack. What do you want? Can't do that, but I'll give you a Reese's. Oh, I promised I wasn't going for Bobo. Okay, so we have friction. Okay, there's a friction force between the contact of the belt and the surface of the pulley. Okay, and this pulley, this rope, the rope or the cord is no longer massless. Okay, we previously assumed that it was infinitely small, and it had no effects on the pulley. But if we now are taking into account the size of the rope, okay, how do we represent that in terms of our forces on our free body diagram? What's that smirk for, Jake? What do you think? What do you think the answer is?
Perpendicular.
Almost? What kind of force?
Normal.
Normal. What kind of candy? You don't want candy. All right. All right. So we have our normal force. Okay. There's a contact between the pulley and the rope. Okay. The rope is applying a normal force onto the surface of the pulley. Okay. What kind of loading condition, okay, think way back to our second module, what kind of loading condition is this? Yeah, it's a distributed. Okay, this loading condition, this is a distributed load. What do you want, Aaron? Okay, it's a distributed load. Okay, so what do we do with distributed loading, distributed loads? Find the result and integrate. Okay, all right, but even before that, to integrate, we need to take an infinitely small piece of the whatever we're integrating across, right? So if we take an infinitely small component of the belt, okay, or of this pulley that has a width of dl, okay, this is infinitely small. Okay, we have two tensions here. Okay, I'll call those T1 and T2 because depending on where we are across the surface of the pulley, it may or may not be P or a 200-pound load. Okay, we have infinitely small axial forces that are applying a tension in the rope. Okay, and we also have our friction. Okay, so we have mu, our friction force at the surface of contact. Okay, infinitely small. We're going to assume two surfaces here. Infinitely small. It's got to counteract tension 1. We also have a normal force 1. All right. We have another point of contact over here. We have our coefficient of friction and our normal force at tension at this point, tension 2. That will indicate with the normal force too. Okay, so we're infinitely small, and this is what we're integrating across. Okay, but the nice thing about ropes, about pulleys, is we don't have to integrate across the surface. Okay, that's a hard mathematical tool to do, right? There's a nice equation that relates the tensions, how they change depending on the point of contact. All right? So if we're going to analyze this system, this infinitely small piece of the pulley, okay, we will indicate that this is an angle between T2 and the horizontal of alpha. Okay? But if this is an infinitely small piece, okay, what is actually true about that alpha?
It's the same, like, throughout the system.
It is the same, yeah, Carson?
0.
It's almost 0. It's incredibly small. Okay, what do you want? Kit Kat, Whoppers, Reese's, or Hershey's? Kit Kat. Break me off a piece. Okay? It's infinite. It's almost small. So there's a thing called the small angle approximation that we will use to derive the relation between the two tensions. The small angle approximation, okay, alpha isn't actually 0, but it's so small that the cosine of alpha we will assume is 1. Okay, and the sine of alpha is 0. Okay, Carson said it is 0. Okay, that's what we're assuming. Okay, but it's not. And that's what we represent with the small angle approximation. Okay, there's a neat lab in dynamics that you guys will do dynamics 2 that you will do next year. So you'll forget everything I said right now. Okay? But you actually test this with a rigid body. So that's kind of neat. But if we assume that our angle alpha is so small, okay, that our cosine is essentially 0, okay, we can now apply our equations of equilibrium. Right? It's a machine. We know it needs to be in equilibrium. So if I sum the forces in the x, okay, when alpha is 0, what is in that equation, Adams? So times cosine alpha, okay, we'll assume that that's 1. So we don't need to put it in the board. Does that make sense, though? So negative T1 plus T2 minus N, angle's still alpha. Are you talking about this N1 or this N1? This one or this one? Okay, if alpha is 0, okay, our friction force at the point of contact over here on the left is horizontal, and this normal force is vertical. Okay, with the small angle approximation. So this N1 is actually my friction force. I need to multiply it by my coefficient of friction, of static friction. Okay? So how would you add this other friction force at the second point of contact? N2 mu? Is that positive or negative? Look how it's oriented. Okay, we're counteracting the tension 2. Negative. All right? Good job. Okay? What piece of candy do you want? You don't want any candy? Okay. Okay. So we have minus T1 plus T2 minus N1 mu minus plus N1 mu minus N2 mu. All right? Everyone agree? Okay. So we can do some rearranging here. Get T2 minus T1 minus mu times N2 minus N1 all equals 0. All right? So the change in tension is equal to the friction times the change in the normal force. Okay? So these tensions are not constant. Okay, but it is equivalent to the change in normal force. All right? And so to relate those two tensions, okay, that's what you read about last night. And there is a nice equation that we can use, okay, that is equating the relationship between T2 and T1, okay, two tensions, is equivalent to E mu times beta. Okay, who remembers from their reading quiz? Okay, what is beta? Did anybody do the reading quiz? What's that? Was it on the reading quiz? No. Did you read about belts? Yeah. Was this equation on the reading quiz? Yeah, it was. They didn't explain what beta was? I read it in July, so I don't remember.
I looked through beta when I read it.
Okay, yeah. Well, perfect. Then no one gets candy. Okay, beta is the angle of contact. Okay, the angle of contact between the two tensions. All right. So this equation only holds for a pulley with two tensions on it. Okay, this beta is the angle of contact between those two tensions. All right, And this E, okay, that's just our Euler's constant. That's equivalent to 2.718, on and on and on. All right? So this is a very handy equation that relates the tensions in two chords by the angle of contact and their coefficient of friction along that surface. All right? So memorize this. Okay? I'm not going to give it to you on an exam, but you will need it. All right? And there is an important thing to note, okay, in this equation, and that is that T2 is always greater than T1. Okay? And that's because we're using the function of Euler's constant in this. Okay? So we need a fraction that's greater than 1. Okay? T2 is always greater than T1. And that comes with some intuition with your problem. Okay? Sometimes it's not always clear, so you might have to take a stab, okay, and make sure. And that'll make more sense when we work an example, all right? Or if we actually finish our first example. Okay? So we were asked to find P. Okay? So if we were given a coefficient of static friction to be 0.5, okay, on a pulley system, okay, and we have this handy equation, okay, we're given mu, we're given one of these tensions, we need to find beta. So who has a guess on what beta is? I've heard 30 and 150. Okay, who said 150? Carson, why'd you say 150?
I'm not super sure if it's right, but I did because it's 30 degrees from being like 180 degrees.
Right? So we're horizontal. We're horizontal there, okay, and we're coming off at a 30-degree angle. Okay, so your guess is right, that our point of contact is 150 degrees. Okay? So 30 is a fine guess, right? But look at the problem. If we had a contact angle of 30 degrees, there would need to be some tension, okay, that would make an acute angle. Right? And that, mechanically speaking, wouldn't maintain equilibrium. All right? What kind of candy do you want, Carson? Kit Kat again. Oh, terrible throw. Nice catch. All right? So beta is 180 minus 30 degrees. Okay? But because we're using Euler's constant, we need to be in radians. Beta is always in radians. Okay? Always, always, always in radians. So we multiply by pi over 180. All right? And that's equivalent to 2.62 radians. Okay? So now we have beta. All right? So who can set up the equation to solve for P? Yeah, Jack?
Is this for the pulley or for the belt as a whole, or is this just for our infinitely small segment?
Belt at a whole, okay? Because we're assuming those 2 points of contact. Okay, is that normal force is changing between those two forces, those 2 points of contact. Okay, because that friction force, that coefficient of friction is constant. Okay, we can relate the tension at those point of contact. Yeah, Aaron?
Wouldn't it just be like T over E to the...
let's keep it in, don't do algebra right away. Let's keep it in T2 over T1. Yeah, Keenan?
Would, because you already know 200, could you just put in?
So what, let me rephrase, okay? Is 200 in this case T2 or T1? T2, okay? Because what we asked earlier, it has to be larger than T1, okay? Because our P is using our friction force along the surface of the pulley. So we have 200 over T1 equals E to 0.5 times 2.62, all right? So get your calculators out and someone solve for what P is. Probably should have correct notation here. The winner gets a candy. All the healthy folks over here aren't going to do it. Wow, quick. P equals 54 pounds. Okay, what would you like? Ooh, that's a cheap one. That only had 2. Sorry. They don't have as much, they're malted, so they don't have as much inertia. Okay? All right, so it's a pretty straightforward equation, okay, that we're just relating the tension between the 2 points of contact, okay, over the surface. All right? So now, let's work an example from start to finish. It has to be always in radians. Okay, and that's because we are using Euler's constant, and so if you're in degrees, it'll blow everything up. All right? So on this example, okay, we have a guy that's pulling up a 35 kilogram log, okay, over a rock. So he's invented some sort of machine here, okay, to use less force to lift the log, right? Because if he had not used this rock, okay, he would have to use more force because he's taking an advantage. He's letting that rock do some of the work for him. All right? So it's a machine. So how do we solve machines? Analyze individually. What would you like? Jack's on a sugar high. Okay, analyze individually. So you start, remember, typically start on a component that you have the most knowns. So what is that? In this case, what is that? The log, right? So if we draw a free body diagram of the log, right, what are my forces on there? Tension, okay, and the weight of the log. So we have 35 times gravity. Okay, and friction. What direction do we draw friction? Opposing motion, right? Our impending motion is up and to the right. That's how we're pulling it. We must overcome that frictional force that's resisting motion. So I will call that mu n. All right? And we have our normal force that's caused by the weight of the log in the ground. What do you want, Peyton? Hershey's. All right? So can we solve for things? Getting a lot of good answers over here. Okay, how could we solve for it? What would you do, Sarah?
So there are only really 2 unknowns.
There's only 2 unknowns.
Just 7 to x and 7 to y.
Okay. There's
I would tilt the axis so that it's...
excellent. That's probably worth 2 pieces of candy. What would you like?
I'll do Reese's and Whoppers.
Reese's and Whoppers, yeah. Oh, sorry, Kylie. All right. So Sarah said she would tilt the axis along the inclined plane so we can reduce the number of forces that we have to decompose into rectangular components. Okay. You don't have to do that, but I think it's worth your time to get in the habit of that. So if we tilt the axis on the angle of the incline, okay, we can sum the forces in the x to immediately sum the forces in the x and sum the forces in the y, okay, to solve for that tension and that normal force. All right? So who can give me the equation for the forces in the x? What do you think, Will?
T1 minus UN friction.
T1 minus mu n.
And then cosine, n cosine 15 minus
N cosine in the x.
Oh, U of n, right?
Mu of n. And we've tilted our coordinate
Yeah,
system.
we tilted it, and then we're trying to get. Oh.
Right? Because we tilted our coordinate system, okay, to be in this direction, this normal force isn't applying a force in our tilted x coordinate system.
Oh, yeah.
But what is, as Drew
It's our
said?
weight.
Our weight. So we have 35 times 9.81. And how do I get that into my rectangular components of my x?
What?
Say it loud.
Sine 15.
Sine 15. Positive or negative?
Negative.
Awesome. Okay, so you both get candy. What do you want, Will?
I'm alright.
Jake's all right too? These folks on diets. All right. So who can give me some of the forces in the y? What do you think, Asim?
So it's cosine of 35 times 9.8.
Our weight times the cosine, excuse me, of 15. In the y.
Oh, and plus n, normal.
Plus n. Would you like some candy?
The first one's negative.
And the first one's negative, right? Because it's acting in the negative y. Look at the sense of the vector. All right? So get out your calculators and solve for what n and t1 are equal to. Okay? Get in the habit of solving these simultaneous equations because this is going to be common in your belt problems because you often have two tensions, more than one tension that you need to solve for at the same time. Stefan? You got n? Perfect. 335.65 newtons. Yeah, 331 points. Yeah. It's Friday. Would you like some candy? What do you want? Reese's, Kit Kat, Hershey's, and Whoppers. Hershey's. All right. Who's got the tension? Yeah, Sally?
287.
Perfect. 287.86 newtons. Would you like some candy? Kit Kat? The Whoppers are just going down. All right. So we solved for our tension and our normal force. So now we can move on and solve for and draw our free body diagram of this rock and solve for that tension. All right. And so I noticed it this morning when I was reviewing my notes and that this drawing isn't totally correct with how we solved it. Okay, I'm assuming one point of contact here. across the corner, that surface, that curved surface of the rock. All right? So if I draw my free body diagram, okay, I have my tensions, right? And analyzing these tensions, okay, I can now use that pulley equation, right? We know that there is a weight, okay, and there's some normal force, and there's some friction, okay? But there's a lot going on. But with this pulley force, because we know that we can relate how those tensions change over the 2 points of contact, okay, we can use it to immediately solve for the tensions and not have to use our equations of equilibrium. All right? So yet another tool that equips you all to be extremely lazy. Okay? So we have our equation T2 over T1 equals E raised to the mu times beta. Right? So beta, who can give me that? What's that? 165? Okay, between the 2 points of contact. Is it? I got 15. But I now see why you say 165. The 15 is how they solved it. Because I think they flipped, yeah. They solved for this acute angle.
So is that to say that there's a way to solve it with either?
I'm going to have to solve it. Get out your calculator and see if they're the same. With 165 and 15. Right. So in the radians,
Wait, how is it 15 though?
it would just, that's what, I think there's an error that I just caught. Because if we look at the surface of the pulley, we're assuming that this is a pulley, right? We're along a curved surface. Okay, and our point of contact. Okay. Ah, they solved it in the fourth quadrant. That's 15, and that's 165.
Why do we go to the horizontal? The point of contact is on the top.
Because we need to relate that to that, right?
So we not do
75?
75, yeah.
No, and I think it's because, and this is a good question that I haven't thought of. I think it's because we're using Euler's constant, and we need to take it with respect to the first quadrant, because that will affect where you will fall on the unit circle. Okay, but I'm going to have to check the signs. The signs on if it's 15 or 165. Yeah, Carson?
What's troubling about using 165 is that now it doesn't matter at what angle the worker is pulling that rope if you're always measuring from the horizontal.
But that's with the point of contact. So he can pull it. If he pulls it down, is that what you're saying? Or
Because the angle that we're measuring from that horizontal to the point of contact where the log first meets the rock, like that where it first meets the rock, is dictated by the 15 degrees.
you think you know what's going on?
Well, because the points would actually be a lot closer because the angle's so big. So I think they actually did take the angle between the 2 points. It's 15.
Between the 2 points, and it's actually 15. This is great because I haven't.
Because the angle's so big, like the bigger angle you have between the 2 points, like the closer the lines get together around the pulley. Like if the angle is like, I don't know, 0, they'd be on top of each other, but then also if it was 360
Right.
on top of each other.
Yeah.
So 15 would be like a really, like he's pulling this way, the
Oblique
log's going
angle.
this way, 15 would be like a really,
Yeah,
angle.
really oblique angle.
It was really oblique.
Right.
I think that makes sense.
Yeah.
15.
I think, but the math, I'm going to have to check, and I'll be candid about it. I'm going to have to check on the math. But what Carson said intuitively is if you're pulling at a really oblique angle, right, those two force vectors are almost collinear, right? So in this case, they're almost 180, almost parallel, but there is a 15-degree angle between them, all right? But in solving it from the first quadrant, okay, so I'm going to have to check on that, and I'll post my work once I go through the math. Yeah, Nick?
I thought it was just it's 185 and then just 15 is the reference angle. Or 195, sorry.
195 and then 15 is your reference angle. I'm not following that.
Yeah, so you just go around 15 miles. It's 180.
If you go around this way?
No, around like the way that like the unit circle is.
From the top arrow, go counterclockwise.
Yeah.
No, so if you're like in the middle of the leg of the top arrow, it's going horizontal. Yeah, or move to your right 3 inches. Now go counterclockwise 195 degrees is what he's telling you.
Oh, to get to the other.
Go up and to the left in the circle.
I'm not following that.
Like,
All right, we're veering off. All right, let's come back. Let's converge back onto what Carson said. All right, in that these two angles, right, the point of contact between this oblique angle, right, is solved for 15. Okay, but again, put an asterisk because I have a couple of deliverables that I still owe you from last time and today. Put an asterisk. We'll solve for 15. Math never gets easier, remember? Okay, so our 15 degrees, putting it in radians, all right? So if we solve for our tension, okay, is T2 or T1 larger? What do you think? T1 is larger? Why do you say that?
Because like a pulley, like it's at an angle, and the point that's getting moved at the angle is going to have more force acting upon it than force that is acting linearly.
That's correct, but what aren't you taking into consideration?
The friction.
The frictions are different, right? The friction between the log and the ground is greater than the friction between the pulley and the rope. Okay, so to overcome that frictional force, okay, on the ground, this tension, this T2, has to be larger than T1 because that coefficient of static friction is so much bigger than between the log or the rock and the rope. All right, so we have T2 over T1, all right, and that equals E raised to the mu times beta, all right? So who can solve for what T2 is equal to?
So are we going to end up having a worker pulling, pulling harder than you would have to?
Mm-mm.
T2 is bigger than
Look at the weight of the log.
The worker would be
The weight of the log, okay? The tension that they will be pulling with the log is still going to be less than that actual weight. Okay, so there's two components here. It's not just a direct input. Anybody plugging it in? Did you get it?
Yeah, I got 320.
That's perfect. Why didn't you say it louder? Can you solve for T2 to be 320 newtons with an asterisk till I check my unit circle? What would you like?
Reese's.
Reese's.
Thank you.
All right. Any other questions on that? Except for the point of contact? And I think it's because of where we have to fall on the unit circle. We need to be in the first quadrant. But I want to check on that before I tell you for sure. All right. So let's set up this problem. Okay, I have to end in a few minutes to pass back the tests. Okay, but let's just set up this problem, and I want you guys to solve it sometime this weekend. All right. So we have two pulleys here. Okay. We have a known mass of 50 kilograms hanging from pulley B and an unknown mass M hanging from pulley C. Okay, and they ask us in part A, what is the smallest value of M that we can hang to maintain equilibrium? Because if it's too small, it's going to fly up, and if it's too big, it's going to fall down. All right? So with pulleys, okay, with this pulley, with this machine, how many free body diagrams are you going to use? What's that?
4.
4? 2, right? If we analyze this as a machine, okay, there's 4 things going on, but the masses, there's nothing really interesting.
Oh, yeah.
Okay, because we know the tension has to be equal to the mass. We can use our pulley, okay, our pulley equation. If I'm analyzing pulley B, okay, pipe B, we have our weight, okay, 50 kilograms times 9.81, and there's some tension between pipes B and C. All right. We also have pulley C. Okay. We have our unknown mass M. Okay. Times our tension in pulley BC. All right. So we can apply our equations of equilibrium, not equilibrium. Okay, we can apply our pulley equation that relates the tensions. Okay, we only have one unknown here. Okay, we can solve for TBC. Okay, using that relationship between the tensions. All right. So I want you to work it. Okay, and I want you to solve in your answer to get your mass. M equals 22.8 kilograms. Okay. So make sure you can work it and apply this equation and solve for that. Yes, Stefan? Will there be a normal force on the rope? There is. Okay, and that's what we derived. But in this equation, because that change in tension is equivalent to the change in normal force, okay, we're relating that change in tension. So we're not taking into account. And that's the handy part about this equation, because we don't have to integrate across that distributed load. It's a good question. All right. Any other questions on pulleys? Yeah, Will?
I'm kind of confused on how to find the angles. So which angles would you use?
And how to, so look at your points of contact. This one's a little more straightforward than the rock. Okay. So if we have our points of contact, okay, I have 2 points there. All right, so what's your point of contact? Where did I go? Lost it. Okay. We have some beta angle there. Okay. And then you have an acute angle between your points of contact on pulley A. Right, so it's always up between the points of contact. Does that make sense?
I want to remember the equation.